How to build an AI platform for ultra-low latency algorithmic execution for scalping. Building an ultra-low latency AI-driven algorithmic execution platform for scalping requires a careful combination of high-performance infrastructure, optimized data pipelines, and specialized quantitative models. Below is a high-level overview of the considerations, architecture components, and best practices for building such a platform. 1. Infrastructure and colocation. Exchange colocation or proximity hosting. What? Deploy servers physically close to the exchange matching engines, often in the same data center. Why? Minimizes round-trip latency for market data and order placement. Considerations. Exchange-specific compliance and approval processes for colocation. Potentially higher operating costs, but essential for ultra-low latency strategies. Ultra-fast networking and hardware. Network. Use low-latency network interface cards, NICs, with kernel bypass, e.g., Solarflare, Mellanox, to reduce overhead. Hardware acceleration. Field programmable gate arrays, FPGAs, for feed handling or partial inference. GPUs for training or inference if your AI models benefit from parallelization, though not always optimal for ultra-low latency inference. Specialized CPU instructions, e.g., AVX, SSE, for numerical operations. High-performance servers. Bare metal or low-level virtualization with minimal overhead, e.g., single-socket servers with high clock speed. 2. Data acquisition and preprocessing. Market data feeds. Direct feeds. Subscribe to the exchange's native feed versus aggregated vendor feeds to reduce latency. Multicast/TCP. Most exchanges use multicast for distribution. Ensure your systems can handle packet loss and real-time decoding. Feed handlers. Optimized parsers. Use low-level languages like C++ or Rust for parsing and normalizing raw market data. Message queues. Optional. Use a high-speed messaging layer, e.g., Redis, 0MQ, AARON for internal data distribution, but be mindful of added latency. Feature engineering in real time. Sliding window aggregations. Maintain rolling metrics, e.g., moving averages, order book imbalance in memory. Event-driven. Use event-based frameworks that trigger computations on each market tick rather than batch-based approaches. Hardware/software optimizations. NUMA awareness. Pin processes to specific CPU cores and memory regions for consistent performance. Kernel bypass. Use frameworks like DPDK, Data Plane Development Kit, or RDMA to reduce network stack overhead. 3. AI or ML model design and training. Model selection. Classical versus deep learning. Classical ML, random forest, gradient boosting might suffice for short-term market patterns and can be lighter weight for inference. Deep learning, LSTM, CNN, transformers could capture complex temporal dependencies, but may introduce inference latency. Hybrid approaches. Combine signal generation from advanced ML with rule-based checks to reduce false signals. Data sets for training. Historical data. High-resolution limit order book data, tick by tick, top of book, full depth, etc. Feature enrichment. Short-term price patterns, e.g., microstructure features. Velocity/acceleration of price changes, order book imbalances, or queue position. Event-based triggers like large trades or quote changes. Backtesting and simulations. Ultra-high resolution, tick-level or microsecond-level simulation environments. Latency modeling. Include realistic round-trip latencies and slippage in simulations. Stress testing. Evaluate model performance in extreme market conditions, e.g., sudden liquidity dry-ups. Model deployment. Compiled inference. Use frameworks like ONNX, TVM, or TensorRT for neural nets to accelerate inference. Low latency embedding. Deploy the model as a statically compiled library in C++ or Rust if needed. 4. Real-time decision engine. Decision logic. Signal thresholding. Translate model output into buy/sell/hold signals based on confidence thresholds. Risk management. Real-time checks for position limits, max daily drawdown, or liquidity constraints. Adaptive logic. short-circuit or skip inference altogether if market conditions do not warrant trading, e.g., low volatility periods. Order execution algorithms. Scalping specific tactics. Aggressive limit orders at or within the spread. Immediate cancellation if not filled quickly. Pegging strategies that follow best bid/ask. Smart order routing. If trading multiple venues, evaluate where to place orders to get the best fill probability. Distributed architecture. Active/active setups. Multiple algorithm instances running concurrently with a failover plan. Stateless versus stateful components. Keep stateful logic, like open positions, partial fills, in shared low-latency storage, e.g., in-memory DB, so that any node can act upon the most recent data. 5. Monitoring and risk management. Monitoring latency and throughput. Real-time metrics. Monitor end-to-end latency, e.g., from market event to order on the wire. Micro benchmarks. Track individual steps, feed handling, inference, order routing, etc. for bottlenecks. Performance tuning. Profiling tools. Use perf, flame graphs, or specialized performance profilers to identify hotspots. Feedback loops. Immediately detect if the system's latency is climbing and degrade gracefully or pause trading. Risk checks and circuit breakers. Real-time exposure checks. Keep track of net exposure, max drawdown, or threshold breaches, e.g., abnormal P&L swings. Adaptive shutdown. Automatically halt trading if catastrophic conditions arise or system anomalies are detected. Regulatory compliance and logging. Audit trails. Store a detailed log of market data, model signals, and orders for compliance. Compliance. Adhere to exchange/SEC/FINRA regulations if operating in relevant jurisdictions. 6. Key best practices. Keep it simple, then optimize. Start with a straightforward, robust pipeline. Introducing complex AI models too early can obscure performance bottlenecks. Modular design. Separate data ingestion, feature computation, model inference, and order execution into well-defined modules. This helps isolate and fine-tune latency hotspots. End-to-end testing. Deploy continuous integration, CI, and continuous deployment, CD, pipelines that can run regression tests and latency tests. Fail-safe/fallback mode. If the AI model or real-time engine fails, have a rule-based fallback or simply pause new orders to avoid uncontrolled exposure. Incremental deployment. Gradually roll out changes in production with canary releases, starting with a small share of capital to limit potential losses. Conclusion. Building an ultra-low latency AI platform for scalping requires deep expertise across multiple domains: high-performance computing, networking, financial market microstructure, quantitative modeling, and robust risk management. The technology stack is often a mix of specialized hardware like FPGAs, low-latency NICs, and software optimizations, kernel bypass, C++, or Rust code. From data ingestion and real-time feature computation to fast AI inference and order execution, each component must be continuously profiled and optimized. Finally, strong governance in risk and compliance ensures that high-speed strategies remain safe and within regulatory bounds. By carefully combining these elements, exchange colocation, optimized feed handling, real-time model inference, and carefully crafted order execution logic, you can build a platform capable of scalping with minimal latency overhead and robust risk controls.